Suppose that I have my little yellow ball attached to a spring, and I pull it down and let go. Then the ball would just go up and down. Now, I want to think about the energy this time. Let's say suppose that as it moves up and down, let's say that at a certain time, the ball is here. Now, when it is here, let me suppose that it's here at a certain time. So when it is here, it would be stretched by a certain distance of x. So we have seen in an earlier session that the work done, the work that is needed to stretch it by this amount, right, that's equal to half of the force times the extension. If you remember, we had Hooke's law. With Hooke's law, F equals to Fx, where we plotted force against x and say that, right, it is a straight line, and that if you pull the string out, as x increases, the force increases, and for every short distance of x that you pull, for every short interval of x that you pull it, you do the force is about the same. So the amount of work that you do is force divided times the change in x, right, the movement in x. So therefore, which is approximately equal to the area of this rectangle. And if you keep adding up all the forces for all the many areas, you would end up with this area of a triangle. And so therefore, the work done when you pull a string, the spring out by a distance x, is half base times height, which is half of x times f. So that's how we got this. And in terms of Hooke's law, f is equal to kx. So you substitute kx into the f here, you get half kx squared. And the work done, all right, the work done when you pull this out, if you release the spring, the mass, the ball, would start moving back to its rest position. Okay, so it gains kinetic energy, but as it moves back to its rest position, the x decreases back to 0, so the potential energy drops to 0. So this the work that I've done in stretching the spring is converted back into the kinetic energy. So this means that the work that was done is it has not just disappeared. Okay, and when I pull it out to this distance x, the work that I've done is actually stored in the spring. Now this energy that is stored in the spring and that gives the kinetic energy once I let go is the potential energy. It's called the potential energy. In the case of the spring, it is called elastic potential energy. Okay, and that's half kx squared. So we have potential energy here, and we also have kinetic energy. We have kinetic energy since this is moving. When it moves, it has velocity. And that's given by half mv squared. So as we have seen, if I pull it by a certain amount, okay, it has potential energy. But if it's at rest at that distance, then there's no kinetic energy. But once I let go, it goes back to its rest position. So the potential energy goes towards 0 when x goes back to 0. But instead, I would have kinetic energy since as it goes past the rest position, it has the maximum velocity, meaning that the potential energy would be converted to kinetic energy. And if it overshoots the rest position, it will slow down again. What happens is that if the ball, as it overshoots the rest position, it will compress the spring. Right? So it will do work on the spring, and this work is again converted into potential energy, and it slows down, meaning that the kinetic energy goes to zero. Okay, and then the motion repeats itself. So it looks like as the ball oscillates, the potential energy and the kinetic energy keeps changing into each other. So let me try and plot a graph of these two types of energies. Right, I'll start with the potential energy. So let's say I pull it out and I let go. So when I pull it out, I would have potential energy. Okay, I would have the maximum potential energy when I pull it out. And when I let go, as it springs back towards its rest position, the potential energy should fall to zero at the rest position. But as it overshoots its rest position and start compressing the spring again, it should go up again. Alright, go up again to a maximum where it stops, and then the spring pushes the ball back down, converts the PE to energy, so the PE decreases again. So it keeps doing this. Okay, now let me just make some note here so I know where I am. This is when I stretch it out. So this is at the maximum displacement. Okay, that where the potential energy is zero is at the rest position. Okay, and that's the maximum displacement again on the other side and the rest position and so on. Now let's look at the kinetic energy. At the maximum displacement, the kinetic energy is zero because it's instantaneously at rest there. So that's where the KE is. So as I let go, the ball accelerates back towards the rest position, and the velocity is biggest at the rest position, or as the momentum carries it past the rest position. So at the rest position, I have maximum kinetic energy. So the graph should look like that. Now you can see this opposite trend. Whereas the potential energy comes down, kinetic energy goes up, and they get converted into each other. And as the ball zooms past the rest position, it slows down, compresses the spring, KE gets converted back into PE. So KE decreases back to zero. Okay, so another interchange. KE changed to PE, and so on. Just imagine that. So this is KE, kinetic energy, and that is PE, the potential energy. So you have this interchange with one another. And one last thing, conservation of energy. We need to talk about that. Now KE changed to PE, PE is changed to KE. So at any point in time, we must expect that the total energy would stay the same. It remains constant. Right? Because energy cannot be created or destroyed, it can only be converted from one form into the other and maybe back again. So this is the total energy. Total energy, KE plus PE, remains the same. So if I plot a graph of the total energy, it would be a horizontal line. This will be it. So at any one point, if I add, say at any point in time, say this point, and let's say this is time. If I add the kinetic energy to the potential energy, I must end up with the same answer, no matter where I am.